And we're on. Okay. Now, this is a lesson on intermolecular bonding. And I don't know what you want to know about it. I'll do what I can, but just an overview, really, of intermolecular bonding. All right. Now, obviously, let's start off with something nice and easy. Bonding. Okay. What are the bonding types that we deal with? Well, very roughly speaking, we have ionic, and then we've got metallic, and then we've got covalent. I know you know this. It's just somewhere for me to kind of start the lesson. Okay, ionic is obviously positive and negative ions. Okay, so positive ions and negative ions. Metallic is positive ions only. All right, like this. All right, surrounded by, as you know, the sea of electrons. So these have electrons everywhere. All right, this is ionic, but this is not ionic. Even though it has ions in, we don't regard this as ionic. Covalent, now obviously covalent is a sharing, but we split up covalent into two, where we have giant and simple. Giant are these huge structures, okay, like diamond and graphite. And simple are small structures like water. Okay, so these are formal bonding types. Okay. Now, I think that's it. I can't think of any more. I'm sure there is one that I've missed out that's bound to be. But there you go. These are the types of bonding we deal with in chemistry. All right. Now, so which one are we looking at today then? Well, believe it or not, we're not looking at ionic. Okay, that's inter. This is electrostatic interactions between the ions. But we're not looking at that today, so that's a no. We're not looking at ionic. This is also electrostatic. Okay, because it's positive and for attracted to negative, but we're not looking at these. These guys, well, these are sharing electrons. These are covalent bonds, aren't they, between the atoms? These are giant structures. We're not looking at this one, but we're looking at this one. Now, between the atoms here is covalent, but between the molecules are the IMFs. And that's what we're looking at today. Are we reasonably okay that's what we're doing today? Is everyone happy with that? This is all right. Well done, Melissa. Right, so let's get on with them then. Whoops, what the hell's that? Right, let's move this up. Okay, and basically, there's three types of intermolecular forces. Okay, there's three types. Okay, and let's go in strength. The first one is known as I don't know, Van der Waals, I'm going to call this, which is weaker than dipole dipole interactions, which is weaker than hydrogen bonds. These are the three, really. Now, the term Van der Waals, in different places, it means different things. Okay, but generally speaking, what I'm going to say is we're going to separate it up into Van der Waals, dipole, and hydrogen bonds. And my definitions here are what Cambridge expect of you. Van der Waals can be called different things. There's things like London forces, dispersion forces, but we don't tend to use that at our level. All right, so let's tick off the first one, Van der Waals. Now, I'm sure you've heard me in class talk about this. Let's have a look at a methane molecule with another methane molecule. Now, these, because the electronegativities of carbon and hydrogen are similar, they're very similar in fact, we say that methane has not got a dipole. Okay, in other words, there's no permanent dipole in a methane molecule. All right, because everything's kind of the same. Carbon and hydrogen have very similar electronegativities, and because of that, there's no overall dipole. All right, but because of the vagaries of quantum mechanics, sometimes you can get more electrons over on one side of the molecule than the other. So purely because of a random effect. Oh, Jonathan wants to come in. Okay, there you go. Welcome, Jonathan. Because of this kind of random effect of electrons, you tend to get more on one side than the other side. Okay, so over here is delta minus. There is more electrons, and because there's more on one side, there's got to be less on the other, less electrons on the other. Now, this situation here is a dipole. A dipole means two poles. All right, I'm glad your crush is here, dear, the lady. That's good. Right, now this is a dipole, isn't it? Let me give it a nice color. This is a dipole. Dipole means two poles. All right. So, what type of dipole is this? Well, this is a temporary dipole. All right. Now, another way of saying temporary dipole, it exists for a tiny, tiny moment of time. It's also known as an instantaneous dipole. Now, you'll have to look at the syllabus because I honestly can't remember which term they prefer. Maybe it's instantaneous or maybe it's temporary. I don't know. I honestly don't know. All right. But it's the same thing. It means the same thing. Now, this dipole here, this temporary dipole or induced dipole, will induce a dipole in a molecule next to it. So it will scare electrons off to the other side of the molecule, and it will create a dipole in a neighboring molecule. So we also have a dipole here. This is another dipole, but this dipole is induced. Okay, it's been induced by the other dipole, and the delta negative on one side will be attracted to the delta positive. Not really, dear. I'll explain why in a minute. But you'll get an attraction for the negative side, for the positive side of the other molecule. Okay, and this interaction here is known as a van der Waals force. It's a van der Waals interaction. Okay, so the first dipole here was an instantaneous. Oh, is that how you spell it? Dipole. And it created an induced dipole. Now, if you look at the syllabus, I think there's something about this in the syllabus. Instantaneous dipole has the initials ID, and induced dipole has the initial ID. Okay, but annoyingly, ID isn't the same as ID. All right, I hope that does that make sense now? You'd think it would be, but it's not. One ID is instantaneous, the other dipole is induced. All right, okay, cool. So the first type of interaction is instantaneous dipole, induced dipole, and we call this an interaction. Okay, it's often, well, I don't want to confuse you, but it's often known as a coupling as well. ID coupling. All right, in other words, they come together. Now, that's the first. This is the weakest. Why is it the weakest? Well, because these guys here, these instantaneous dipoles, they only last for frighteningly small times, for very short times. Okay, but don't forget you've got a trillion molecules, haven't you, floating around. So it's instantaneous, temporary, induced. Don't know what that means, dear. Yeah, I think I get what you mean. You could either call it. I think I'm getting you, dear. But let me see. You could call this a temporary dipole, induced dipole interaction, or you could call it an instantaneous dipole, induced dipole interactions. These are the same. Does that make sense? Yeah. That's you can do that. All right. So as I was saying, they're very weak interactions because the instantaneous dipole only lasts for a very short time. But don't forget, in the trillions and trillions and trillions of molecules you've got, there's always going to be loads and billions of these dipoles happening. Because when you have a huge number of molecules, there's going to be a net force between the molecules, and that's known as a van der Waals force. Now, obviously, because it's because electrons do this, don't they? Basically, more electrons in a molecule. The more electrons you have in a molecule, this is going to lead to more chances of an instantaneous dipole. Instantaneous dipole. All right. More electrons is very important. So the greater number of the electrons, the more electrons, the greater the van der Waals forces. Okay, more electrons, greater van der Waals. Okay, now we see, where do we see this? Well, we see it commonly in the noble gases. I can't remember what's first. I think it's neon. No, it's not neon, is it? It's helium, neon, argon, I think. Okay, so helium, neon, argon. Jonathan, ain't Van der Waals. Yeah, they are the weakest. Okay, these are Van der Waals. Eh? They're the weakest of interactions. So if you think about the interactions between a helium and another helium, and a neon and another neon, and an argon and another argon. Hold on. Everyone's asking too much. Oh god, now Tandy wants to come in. Right, here we go. Right, so let's go with Jonathan. Are Van der Waals the weakest? Yes, they are. So there is levels to the weakness. Yes, yes, Jonathan, there are. There's weaker Van der Waals and stronger Van der Waals. Do all non-pop? Oh, do you think it's yes? There's levels to this. Is my voice okay? By the way, it sounds a bit funny to me, but it always sounds funny to me. Do all non-polar have this type? Are there? Are there? I think you've been doing some Setswana then, the lady. Are there is levels to this? Yes, there are. Yeah, there are levels to this. Normal funny. Thanks very much, Wilson. Right. So the van der Waals between helium atoms and the van der Waals between neon atoms and the van der Waals between argon atoms, it's the same type of force, but as you go down, the strength of the van der Waals increases. Why? Because the number of electrons increase. Does that make sense? All right, and because there's more electrons, there's more chances of forming these interactions. Okay, so a consequence of this is, by the way, these are all of these we're going to talk about are IMFs. The IMFs increase between helium and argon, and one of the ways we can see this physically is we can see an increase in boiling point. Okay. Now, melting point has something to do with it as well, but boiling point is a better indicator of this type of bond. Okay, you might think why solids have different interactions. They've got other things going on in solids. So a better indication of intermolecular forces is boiling point, not melting point. All right, so we got increased van der Waals going down. So are we good with that? So there's one chance there. Okay, where are we now? Oh gosh, I've lost my. Oh, there it is. I think yeah. What on earth? Where's my mouse gone? My mouse has disappeared. Oh well, never mind. Let's see if I can. Oh, it's back. I think there it is. No, it's not. Level Hong wants to come in. And I don't think I. Oh, there we go. My mouse has just come back. That's weird. The mouse disappeared. All right. So one consequence, one thing here is the noble gases. Another one, another friend of ours that proves this is the halogens. These are the halogens. Okay. Now fluorine, bigger, and iodine. Forget bromine. Oh, let's forget. No, let's start with chlorine, bromine, iodine. Okay. Now, obviously, here we have this, and here we have this. I'm trying to draw them bigger as we go down. Abotle's coming now. Let me say hello to Abotle. Tumela, Abotle, how are you? Hope you're good. All right. So this is chlorine. This is bromine. And this is iodine. Oops, daisy. Oops, that's not good. Right, now the interactions between these guys, chlorine and chlorine, bromine and bromine, iodine and iodine. Okay, we can see this here, can't we? So as you go down, the melting points and the boiling points increase. Okay, now as atomic radius has no effect on boiling and melting point. It does. The thing is, well, I'll tell you that in a minute, Jonathan. That's a quite good question. Right. So these are the Van der Waals here. Well, let's get a different color. These are the Van der Waals. All right, and as you can see, they get stronger as you go down, and that's why chlorine is a gas, bromine is a liquid, and iodine is a solid. Now, Jonathan's thing is this: atomic radius has no effect on the melting and boiling point. So, does anyone want to answer that quickly? It's not. It's not. Oh, you're not wrong. I'll come to that in a minute, Basadi. You're not wrong, Jonathan. But the thing is, if you have more electrons, your atomic radius is going to be greater anyway. Does that make sense? So it's not the actual atomic radius that gives you higher van der Waals. It's the fact that you've got more electrons that gives you a higher van der Waals. Now, so if I was to ask you what is the effect, what causes the increased van der Waals, your answer should be there are more electrons. But annoyingly, because there are more electrons, your atomic radius is likely to be bigger anyway. Because if you've got more electrons, you're going to be a bigger atom, aren't you? Does that make sense, Jonathan? Are we good? Excellent. All right. Now, I think this is what Basad is talking about. So the Van der Waals increase going down here. But interestingly, and this is what students get confused, the bonds here between the atoms, in other words, what did Basadi call it? The bond energies decrease going down. Group 7. Or 17, or whatever we call it these days. Okay, so this bond is strongest, and this bond is weakest. Yes, exactly. Now, Moss got it right. Now, listen, this is very important. One effect increases going down, but the other effect decreases going down. And this is what students, excuse me, this is what students get confused about. All right, the van der Waals increase going down, but the bond energy decreases going down. Now, why does the bond energy decrease? Well, because the bond length, nucleus to nucleus, the bond length increases, and if the bond length increases, the electron density between the atoms decreases. So the bond energy decreases down the group, all right, but the van der Waals increase down the group. So if I were to do, let's have a look at this. Let's do two graphs here. What am I going to do? Chlorine. If I break up chlorine, all right, I will do this. All right, I'm breaking up chlorine and I'm breaking up iodine and I'm breaking up, sorry, bromine. I'm breaking up iodine. I'm breaking them all up. All right, and now over here, I'm breaking up chlorine. What am I doing here? Chlorine liquid. Oh, that's not very good, is it? What should I do here? Yeah, what the hell? It's a chlorine gas. Chlorine. Oh, not chlorine. What's wrong with me? Get rid of this. Bromine liquid. So bromine gas. Iodine. Solid to iodine gas. Now, there's two effects on it. Going down here and going down here. All right. On the left, we're breaking up the actual bonds. This one is bond energy. On the right, we're breaking up the molecules, aren't we? We're breaking up intermolecular bonds. So this one is, I don't know what we call this, is vaporization, I guess, something like that. We're creating vapors, but it's not quite vaporization. So the point I want to make here is bond energy, as you go down, energy must go in to break bonds. Energy in, and this one is energy in because we're breaking bonds. But as you go down, the energy in to break the bonds decreases. In other words, this one, delta H here, and this one, delta H here, they're both positive. Now, I don't know the numbers off the top of my head, but chlorine, I'm going to say, is about 360, and iodine is about 250. Okay? In other words, to break the bonds between the atoms, it gets easier because of this bond length thing. But in the second case here, to break the bonds between the molecules, energy in increases. Oh, we good. Before I talk about anything else, can we do that? Do we understand that? Dear me. All right, thanks, Basari. Right, now I've missed a few things. Explain the electron density again. I will, dear. I'm also increasing radius bond length with same number of outer shell electrons means lower electron density. Yes, that's right. Exactly. What's the difference between electron density and charge density, and how do they affect melting points? All right, and the Basari says yes. All right, so let's talk about this thing that Wada was asking, I think. Okay, so you've got a chlorine molecule and you've got a bromine molecule. Okay, this is chlorine, ClCl, and this is bromine, BrBr. Now, between these atoms are electrons. There's electrons and there's electrons. All right, now these electrons, because the way we write Cl, and the way we write BrBr, now we write these for a specific reason, don't we? Because this thing here and this thing here is a bond, a single covalent bond, which means two electrons. Okay, so on average, now you don't want to get too complex about this, but on average, in here there are two electrons, and in this bond here there are two electrons. Okay, now if you think of it, the nucleus of the chlorine is here, and there's a nucleus here. Oh, that was nice. There's a nucleus here of the bromine, goes to the nucleus of bromine there. Okay, so can you see that as you go down Wada, I think this is for Wada, as you go down, the bond length increases. Is that clear, Wada? Yeah? Are we good with that? Wada. Wada's gone. Right, so if the bond length increases, the electrons between the nuclei, their density must decrease. So if the bond length increases, the electron density of the bonds decreases. And that means the bond gets weaker. Okay, as simple as that. Electron density between the nuclei decreases, and therefore the number of electrons is the same, but the bond volume, if you like, the volume of the bond increases because the bond length increases, and therefore the electron density decreases. So the bond gets weaker. So Wada is good. Are we good with that? Excellent. Well done, Wada. Now I saw something from Retabili here. Difference between electron density and charge density, and how do they affect melting points? Retabili, do you want to ask something more specific than that? Electron density. When we talk about electron densities, we don't talk about melting points for electron densities. Electron densities is for bond energies. Um, Melting points and boiling points are intermolecular forces, and we generally don't talk about electron densities between molecules. All right, we talk about these vague sort of van der Waals interactions between molecules. What affects melting and boiling points isn't electron densities within bonds; it's the type of interaction between molecules. I hope that makes sense. I don't know if it does, but I guess you'll come back to me. All right. So anyway, all of this rubbish here. Right, oh, we've done a lot actually. Look at that. Done quite a lot more than I thought. Right. So I hope that makes sense. They're van der Waals, okay, and they're what we call instantaneous dipole and induced dipole. So the next ones are dipole interactions. Now, these can be thought of, the nice ones are the hydrogen halides. There's H. Instead of saying molecules and stuff, can you comment on the strength of van der Waals? Yeah, van der. Yes, these ones almost are. Yeah, saying between molecules. Yeah, the strength of the van der Waals increases with increasing electrons. Does that make sense? Not with increasing electron density, with increasing electrons. All right, Van der Waals. It's like a 1980s pop group. Van der Waals. All right. No, but I see what you mean, I think. All right. So the number of electrons increase the Van der Waals. Can we all stop using bad abbreviations? WWV? WWV? What's that? WWV. WWV. I don't know what WWV is. What is WWV? Almosa. What are you talking about, dear? But don't just blame them. What, dear? What do you mean by WWV? I don't know what you mean. Musa, I'm sick and you're killing me off. Oh, yeah. Is that dog, that fat ass dog? You mean Van der Waal? Oh, bloody hell, dear. Let me tell you, Van der Waal. Is there even a W in it? Oh, there is one. Van der Waal. All right. Van der Waals. All right, Van der Waals. I don't know what your question was now. Right. Mosa's angry. Sorry, Mosa. What was your question about WWE anyway? Uh, yes, of course. Yeah, that's right. Mosa. So bromine would have stronger Van der Waals forces. Yes. Didn't I mention that as you go down? Please answer it. So bromine is what? Yes, of course. Didn't I mention that though? Oh, thank you. You were just concluding. All right. I don't know where you got all these emojis from. Do I have emojis? I don't know if I do. I don't. I don't think I do. What can I do? I've got a stick. Oh, I see. Yes, you're showing me. You could. Do you type in threes everything, dear? Like WWV. Right. So we're good then. Can we go? You don't deserve. No, I don't at all. So we understand that. So as you go down group 7, the Van der Waals forces increase. Why? Because of the number of electrons. Okay. This is why very long polymers like polythene and stuff are, even though they're non-polar, they have very, because they're so long, they have huge Van der Waals strength between them because they're very long, aren't they? And they've got huge numbers of electrons in. All right. Oh, interestingly, what am I going to do now? Before we go on to dipole interactions, so let me get rid of this. We are going to come back to this. Don't worry. All right. One thing I didn't mention, and I should have mentioned, is the surface area effects. All right. Now, sorry about that. I should have mentioned this. Okay. Right. The surface area effect. Now, let's have a look at this guy. Yeah, this thing, dear. Now, this thing looks weird, doesn't it? Okay, and it's 1, 2, 3, 4, 5. This is 2,2-dimethyl propane. Okay, and if I were to draw it nicely, in fact, can I? I wonder if I can do something quite clever. I think I've got rid of you for a minute. So let me see if I can get my chem sketch going. Chem sketch. There it is. Sorry, I know. I've turned it off. When I'm on another application, it turns it off for some reason. You'll see in a minute, though. All right. Okay. Okay. Oops. All right. No. Right. I'm trying something quite nice here. I don't know if it's going to work. But there. CH3. 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 All right, now hydrogens. Don't worry, you'll see what I'm doing in a minute. Talk amongst yourselves. Why don't you? I'm making that molecule I've got on the wall there. All right, I'm making 2,2-dimethyl something or other. All right, let me clean up the structure. Excellent. Oh, that doesn't look good. Right. Here we go. Copy that. Put it into the 3D lab. Oh, maybe it's not visit the lab. Oh, that sucks. All right, no. Oh, I don't think it's going to work in this application, I'm afraid. No, I don't want to save that. Right. Ah, that's annoying. Right. No, it's not going to work. My ChemSketch is I've only got the cheap one. I've got another package, but it takes too long to open up. All right. Anyway, if you were to look at 2,2-dimethylpropane, because of the 4 methyl groups around it approximates a sphere. Believe it or not, this molecule, okay, because you've got 3 methyl groups around thingy, so it approximates a big sphere. All right, it isn't a sphere, but it approximates one. All right, so there you go. There's 2 there. All right, and let's have a look at pentane. Pentane, 1, 2, 3, 4, 5. This guy approximates a big sausage. Okay. Now they're isomers of each other. You probably know where I'm going with this. All right. But this guy approximates like a sausage. All right. And this guy approximates another sausage. Now, which one has a higher boiling point? Well, the pentane has a higher boiling point. This one has a higher boiling point, and this one has a lower boiling point. Now, the reason for that is you can't argue this one away in terms of electrons because both of them, they're isomers of each other, and that means they have the same number of electrons. Okay, but you can argue it in this sense. In the spherical one, in the spherical one here, the surface area contact is quite small because 2 spheres touching is quite small. But in the sausage-like one, you can have quite a few points of contact. All right. So in this one, the one at the bottom, you have higher van der Waals forces because of surface area contact. Is that okay? Are we good? Are we good? Are we good? Okay, so I meant that. I decided that's what I meant by surface area contact. Okay, so bear that one in mind as well. So if someone says to you, why does 2,2-dimethyl propane have a lower boiling point than pentane? You can't argue in terms of electrons because they've got the same number of electrons. How were we supposed to know they're sausages or spheres? Well, dear, you've got to. Basically, it's this. Okay, for isomers, and don't forget this will only occur with isomers. For isomers, more branching means less surface area contact. Okay, so if I were to give you pentane, okay, which is this 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, and methylbutane, 1, 2, 3, 4, and 2, dimethyl propane. 1, 2, 3, 4, 5. Well, you've got to have a bit of an imagination here, but you've got to realise that this one will have greater surface area contact than this one, and this one will be somewhere in the middle. So look, I don't know the melting and boiling points of pentane, but I'm going to guess. I'm going to pretend pentane is 60. Methylbutane might be 50, and 2,2-dimethyl propane might be 40. Does that make sense? So the more branching, the less surface area contact you'll get. All right, now we've got to push on now because we've still got 2 to do. Bloody hell! All right, so we're good with van der Waals. All right, excellent stuff. Right now, the next one we were going to do is dipole-dipole interactions. Now, as Moses said, Um, when I write this, I should really write permanent dipole, permanent dipole. That's a better description, isn't it? In other words, PD, PD interactions. And I think that's how the syllabus mentions it. Check the syllabus, everyone. Make sure you know what you're looking at. Now, this one is best exemplified by the hydrogen halide. So there's HCl, and there's HCl. All right. Now, because there's a difference in electronegativity, we get dipoles, dipole-dipole interactions. We get this when we have a difference in electronegativities. That's what you got to know. All right. Now, if you have a difference in electronegativities, you have an yes, they do. Everything does. Very good point as well. And I should have mentioned that. Um, Listen, everyone, Moss is quite right. Whatever the molecule, all right, they all have instantaneous dipole, induced dipole interactions. All of them do. Everyone does. But when we talk about HCl, all right, oh, did I really, dear? No, lady, what did I say? I'm sorry. I missed you. I, no, lady, I don't hate you. But what's wrong? What did you ask, darling? I must have missed it. No, lady, you ask your question again. I'm very inclusive, dear. Everyone gets a go. Most I don't hate her. Now, what was I going to say? Everything has instantaneous. What was I going to say now? Instantaneous induced dipoles. All of them do. Everyone does. However, we talk about the major interaction. Okay, so HCl and HCl does have IDID. It does have IDID. However, it's not the major interaction between the two molecules. Does that make sense? In fact, if you were to do it percentage wise, probably of the intermolecular forces between HCl and HCl, 90% of it is permanent dipole, and maybe 10% is IDID. Does that make sense? There is always IDID though, always. Okay, but we always talk about the major interaction. Okay, so if you ever do anything in life, I don't know what, but if you're a doctor of I don't know, doctor of mathematics, and someone mentions your IGCSE in mathematics, no one really cares about the IGCSE, but you have it, don't you? All right, they're looking at the major interaction. Okay, so you're quite right. Everything has IDID. But let's get back to this. It's a difference in electronegativities. And if you have a difference in electronegativities, you have an, now this is important, you have an uneven electron distribution. Now, an uneven electron distribution, does anyone know what we call such a bond? If you have an uneven electron distribution? I'll give you. Oh, well done, Vasadi. Well done. It's known as a polar bond. Now, please remember that because I saw that in a recent question paper. It's an uneven distribution of electrons. So, because hydrogen and chlorine have different electronegativities, the chlorine is more electronegative, so it's going to suck over the electrons more, and the hydrogen is going to be positive. Delta plus, delta minus. And here, now the strength of this interaction, this guy here, is now the IMF, the intermolecular force. And in this case, it's known as a permanent dipole, permanent dipole interaction. All right. Now, permanent dipole interactions suffer from something. Okay. Now, this may be where the whole lesson came from, really, this problem. Now, you've got to know this. I don't know if we've got enough time to explore this, but permanent dipoles, and geometry. Geometry. Okay. They suffer from geometry. All right. In other words, if the geometry is just right, they can cancel out. All right. Now, IDIDs never cancel out, but dipole-dipole interactions do cancel out. All right. So, and I know a lot of you have been struggling with stuff like this. How about this? CH2, CCl2. Is this polar? is the molecule polar? In other words, is there an uneven distribution of electrons? Now, looking at that, CH2, CCl2, I don't know. I don't know if it's polar. I've got to do what all of you have got to do. I've got to draw the thing. Otherwise, I'll get confused. So I'm going to draw it CH2, CCl2. And once I've drawn it, yeah, that's polar. Oh, what am I doing? There must be a double bond, mustn't there? There must be a double bond there. All right. Now, how do I know it's polar? Well, because this side of the molecule contains two electronegative elements, and this side doesn't. So this side of the molecule is going to be delta plus, and this side of the molecule is going to be delta minus. We draw these by doing this, by the way. We put a big arrow over them, like that, and we say plus. So this is a polar molecule. All right. Now, let's have a look at this. How about this? CH2Cl. Whoops, I keep doing that, don't I? CH2Cl. Is that polar? And I'm going to do another one here. CHCl and CH. Oh, God, I keep doing this wrong, don't I? CHCl. Okay, now let's have a look at these. Let's interrogate these ones. All right, now the CH2Cl, let's draw that. CH2Cl and the CH2Cl. Anyone want to tell me, is that polar or not? Polar or not? Jonathan says, no, not polar, not polar. Are we all for not polar then? This is going to kick your ass then. This is polar. Okay? It is polar. All right? Does anyone want to tell me why it's polar? No, but don't worry, Jonathan. I picked that for a reason, because it does look like it's polar. Oh, they're both at the bottom. It doesn't cancel. Well, it doesn't cancel. That's the point. It doesn't cancel. Why doesn't it cancel? Anyone know? Why don't they cancel? All right. Now, the reason they don't cancel is because they are not, the chlorines are not in the same plane. Okay, now we're all looking at that molecule and we're all thinking, the molecules, they cancel. We're all thinking it's flat. It's not flat. Okay, we're all so used to this idea, aren't we? But they're not flat. Oopsie daisy, look at that weird thing. They're not flat. So let's draw it properly. See, I'm going to draw that there, that, and that, and that. I'm going to put the chlorine there. HH, chlorine there. I don't know. Okay? Do you see what I mean? And because this bond can rotate, the chlorine can go up and down and in the middle. I'm sure there are some orientations where it would cancel, but most orientations it won't cancel. What we're too used to doing, all of us, I think, is we're projecting our 2D images on a flat surface, and we think they're in the same plane, but they're not. So this is not flat. It is not planar. Okay? So this is not polar. What am I talking about? This is polar. All right. So what was the other one? CHCl, CHCl. Now, what about CHCl, CHCl? What about this one? CHCl, CHCl. Is that going to be polar? And everyone's a chicken now. We good? See, would you say it depends on whether? Well done, Basadi. Exactly. Excellent answer. Now, Mosa, you should have seen that. Right. Now, this one is CHCl, and this has a double bond. So this one is polar. But this one is non-polar. Not polar. Oop. Does that make sense? So, what I'm studying. Yes. So, is that polar? Yes and no, depending on what one you're talking about. But the point I'm trying to make here is you've got to look for all of these things. You've got to know, are they in the same plane? If they're in the same plane, do they cancel each other out? Is there a cis trans thing going on? You have to think about all of this. It's not easy, I promise you. It really isn't easy at all. All right, so there you go. No, why don't you know what, dear? You just have to do it, darling. All right. Sucks, yeah. But, Basadi got it. We can all get it. All right. Now, also, you've got to realize this CH2Cl, CH2Cl, and this. You've got to realize, looking at these two molecules, the one on the left contains a double bond. The one on the right contains only single bonds. You've got to be able to see that just from the formula. Yes? Chai isn't chai tea. Right. So, are we good? You've got to see that. Yeah? Got to realise that. All right. Is it hard? Yeah, it is hard. But you know what? There's plenty of past paper questions on this sort of thing, and they'll ask you, especially the multiple choices. So they'll ask you, which ones are polar, which ones aren't. You know what? I've given you quite hard examples, but you can get into them if you look at them. All right. Now, let's have a look at this. If I give you this CH3Cl, and this one CH2Cl2, and this one CCl4. Which one of those is polar? We'll call it A, B, and C. A, B, and C. Which ones are polar? Sally says A is polar. Mosa says A. Butler says A. Jonathan says A. So far, everyone is wrong. I said, which ones are polar? B also. Well done, Butler. Right, and Jonathan. So look at this. CHHCl, polar. CHHCl. This one is also polar. Yeah, they can't cancel each other out, can they? I don't. It's polar. So it's polar. What are you talking about? Did I say something wrong? That's what we said. Most I'm confused. Yeah, no, I didn't think she did either. But this one, since it's a symmetrical molecule, they will cancel out most of. I didn't ask. No, I said. I said which one's a polar, Mosa. You're a bit of a fraud today, aren't you? Right? Are we good with that? Anyway, so do you see that? You've got to realise that as well. So this last one. What do you mean by cancelling out? Right, the dipoles in this one. This is non-polar. Okay, the dipoles. If you now, I'm sure you're good at maths, Body Banda. All right. But if you can, you know what? I guess you do maths, but do you do maths A level? Uh, oh, I see. Hold on. So all things which are not on the same cannot cancel out. In this one, oh, you don't do maths, dear. All right. So, of course, I think I mentioned that before. Yeah, the same plane. Now, in this case, if there's two things on the same plane, you need two things on the same plane to cancel out. But look, this is the point I'm trying to make. I know what you mean by that, Basadi. Right now, this case, okay. Imagine you have this. Now, I guess this is IGCSE physics. Okay, you have 2 newtons pulling that way. You have, I don't know, 1 newton or 1 newton pulling that way. And then you have X newtons pulling this way. And you know this angle, and you know this angle. Okay, could you work out what X is? How would you work out what X is? Maybe I'm talking about maths that you don't understand. I don't know. Does anyone know how we'd figure this out? You've 2 newtons one day. Yeah, what you would do is related to the. I don't know. Maybe I'm getting confused. Wouldn't you resolve the forces? Yeah? Isn't that how you do this sort of stuff? So it's pulling this way at 2 newtons. You resolve this force and find out the component of this force that pulls it this way. Okay, I don't know what it is. It's going to be less than one, isn't it? And then if you know what this force is, you figure out what this force must be, and then you resolve this force in this direction. No, oh gosh. maybe maybe I'll shut up with this. All right, I thought, but normally chemists are very good at maths and physics, aren't you? All right, it's good to. All right, so basically, beside anyway, you can cancel out in a three-dimensional system. Yes, it doesn't have to be in a plane, but if two things, but you should look for that. Are the two things in a plane? Yes, and they can cancel out. Are they in a three-dimensional space where they're set? Can they cancel out? Yes. What happens is, yeah, exactly. So if you think about it, and I don't want to scare you, if you think about resolving the forces in this direction, okay, here it's pulling with 1 cl. Here, in this direction, it's pulling with a third of a cl. Here, it's pulling with a third of cl. Here, it's pulling with another third of cl in this direction. So they cancel out on that plane, okay? Right, are we okay with that? Proxima Centauri is the closest star to us. Yeah, I think you know what, dear. If it's just think about it, look, they're going to cancel. All right, they're going to cancel if there's the same number. If you draw the same, if you imagine a ball and the CLs are tugging from it with the same force, imagine this. Where are we? Above there. Imagine that you've got 4 people around the ball, and you've got 4 strings attached to the ball. Okay. Now here is the ball. There's the ball, and you've got 1 string, another string, another string, and another string. Yes. Now everyone. This is in 3 dimensions, by the way. Everyone pulls with exactly the same force. Let's say 10 newtons. If everyone pulls, whoop, if everyone pulls with exactly the same force, 10 newtons, what will happen to the ball? A botle. What will happen to the ball? A botle. Exactly, so that everyone cancels each other out. It's the same with electronegativity. Yes? Does that make sense? And that's how they can cancel each other out. All right, that's all you got to think about there. If they're symmetrical, there's a chance that things will cancel out. If it's not symmetrical, they can't cancel each other out. If I replace one of these 10 newtons here with a hydrogen, or in this case, a 5 newtons, what's going to happen? The ball is going to move that way, isn't it? Because there's more pulling in this direction now. Yeah, and therefore the ball will move. In other words, if this is a chlorine and this is a chlorine and this is a chlorine, but this is a hydrogen, electrons will be pulled in that direction. Does that make sense? How about that? Are you good? I'll be good. Okay, cool. All right. I hope that makes